for section 11.4, the cross product. So we saw in the last section that Rn, so R2, R3, or the n-dimensional space in general, well, we can define the dot product. And sometimes this is also called the scalar product or the inner product. Now, R3 is special because it has another operation, another product. It's called the cross product. And it's only for R3. The other R's have another operation called the exterior product. So you see inner, exterior. All right, but we won't talk about it. So cross product, only in R3. Okay, so what's the definition? So let's just start with the blind, direct, straightforward definition algebraically of the cross product. So I have two vectors in R3. So I have three components for each, U1, U2, U3, and V1, V2, V3, say. Now, the cross product is a vector. It's not a number like the dot product. It's a vector, and that vector is given by the following coordinates. So I have the coordinates in x, y, and z, the direction of I, j, k, if you wish. And the x coordinate is u2, v3 minus u3, v2. Okay. Then the coordinate in y is u3, v1 minus v3, u1. And in k, it's u1, v2 minus u2, v1. Okay, that seems a bit strange. So how do you get this by computation? How you do it, you do it the same way as you do a determinant of a 3 by 3 matrix. Okay, so this is just a trick to compute it. You put in the first row I, j, k, even though they're vectors. Okay, this is just for the computation. So you put I, j, k, and you write in the first row the u, component for u, then the coordinate for v. And then what you do is you do exactly as computing the determinant of that matrix. Okay? So if you compute the determinant, first you would do, okay, the first, and you'd start with the first row, the first entry in the first row, and you multiply that by the determinant of the square here matrix, so u2, v3 minus u3, v2. So this is what I'm going to write. So I get u2, v3 minus u3, v2, okay, times I. So that's my I coordinate. So you see I have the same thing I had above. You do the same thing for j, but watch out for the second component. So for second component, this is the matrix now. Okay, but watch out for the j, I have a minus, so it's, when you compute the determinant, so I get minus u1 v3 minus u3 v1 j. And you see I get the same thing as above if you include the minus. And then the last one, let's put it in blue, it's for k. So I get this matrix now, plus u1 v2 minus u2 v1k. Okay? So for specific example with two vectors, that's how you do it. You put I, j, k in the coordinates of the example, and you compute as if you compute the determinant of that matrix. Okay? So strange operation, but very nice interpretation, geometric interpretation. So here's the geometric definition, and we'll explain why this is related to what we did above. So the vector u cross v, it's a vector with these three components, is the vector that is both orthogonal to u and v. All right? So that gives you the directions orthogonal to u and v. And the norm of that vector is exactly the area of the parallelogram defined by uv. All right. So what does that mean? So imagine I have u and v. This is u. This is v. Okay, in 3D. Okay, so that's in the plane, if you want, xy plane, and this sticks out. Okay, so u cross v is both orthogonal to u and v. So I have these two angles. So that gives you the direction. Okay, and so you have to be a bit more specific, right? Because if I have this u and v, does this goes down or up? Because these two are orthogonal. So this is not well defined. So which one it is? Is it pointing up or down? Okay, orthogonally from u and v. Well, this is where you use the right hand. So it has to be your right hand. The rule of thumb, but with your right hand. Okay. So you point your fingers with your right hand in the direction of u, then you turn your fingers towards v, and then wherever your thumb is pointing, this is where the u cross v is pointing. So in that case, okay, so this is the right hand. If the fingers point this way, and then I turn them towards v, the thumb's going to point this way. Now if I do v cross u, then the fingers of my right hand are going towards v, then I'm pointing them towards u, then the thumb's going to go down. Okay? So in fact, we always have that v cross u, so u cross v, made a mistake here. If I change the order of the vectors, u cross v is minus v cross u. Okay? And you can see from this, the calculation, algebraically why this is true. One way to see it is if I change two rows, permute two rows of a determinant, right, I get a minus. So that's one thing. But you can check here. So if you change u by v and v by u, because of the order, there's a minus that's going to come out. Okay. So if I change the order, I pick up a minus, and this is just reflecting the fact that, well, there are actually two vectors orthogonal to both. Okay, so you have to pick the right one. Okay, so that's the geometric interpretation for the direction. Now for the norm, well, so what do I mean by the parallelogram defined by u cross v? Well, let's say I'm in the plane defined by u and v. Okay, so I have this vector u and this vector v. Then the parallelogram that we saw essentially when we consider u plus v. So the tip here would be u plus v, right? So if I look at both sides being u, one of them translated, and both sides being v, one of them translated, then that defines a parallelogram. And the area of a parallelogram is exactly like the area of a rectangle. It's base times the height, okay? It's as if I take a stack of books, right? The area would be base times height, but then I just tilt it, the same area. So it's always base times height. Okay, so except the height here will depend on the angle. Okay, so the base is the norm in that picture, the norm of v, and the height, because this is, the height will be the sine of that angle multiplied by the norm of u. Okay, so I get from this that the norm of u cross v is equal to the norm of u times the norm of v times the sine of phi. Okay? Sine of phi, pick the phi to be positive always. Okay? Alright, so that's similar to the dot product, except for the sign I take, except for cosine is replaced by sine. Alright. Okay, so I will justify later a little bit why this is true, that this definition is related to the orientation or being orthogonal and also the norm being the area of the parallelogram. Let's start with a simple example to illustrate that. Let's take the two vectors being the basis vector in the xy plane, 1, 0, 0, 0, 1, 0. Okay? So I is the unit vector in the x direction, and j is the unit vector in the y direction. Now, if I do I cross j, using my definition, my computational trick, I put ijk, I put the entry of I put the entry of j. Now, if I do the determinant of this, well, I'm going to get 0 for I, 0 for j, and for k, I get 1 minus 0. So this is just k. All right, so the direction is consistent with the rule of thumb we had. If I put my finger as the direction of I, turn them towards j, the thumb is up. This thumb is up. And the area of the parallelogram defined by I and j is simply a square here, and there's a square of length 1 on each side, so it's 1. Okay? So that's the simple example. If I take j cross I, and I follow the rule of thumb, my fingers of my right hand goes towards j, I turn my fingers towards I, and the thumb is pointing down, so it's going to be minus k. Okay? All right. Now, two questions. Why is U cross V orthogonal to U and V? And why is the norm of U cross V being the area of the parallelogram? So let's explain that a little bit more. Now, how do I know that U cross V is orthogonal to U and V? So let's do it with U, and V is the same. Well, okay, so this is U dot, so what U cross V, let's do it again with that with the trick. So I get that is U2 V3 minus U3 V2 in the x coordinate. And then in the j coordinate, I get U3 V1 minus U1 V3. And the z coordinate, I get U1 V2 minus U2 V1. All right? And this U is coordinate U1, U2, U3. And then I do the dot product. And if they're orthogonal, this should be 0. So I get U1 times the x coordinate of the dot product plus U2 coordinate of the cross product. Same thing here. All right. Okay, and now you do some cleaning. So I get U1, U2, V3. Okay. But here I get minus U1, U2, V3. So I get 0 for this guy. Same thing here. U1, U3, V2 as a minus. And U1, U3, V2 as a plus. So I get 0. And 0 also for the last one. You can check. So U is orthogonal perpendicular to U cross V. And it's the same thing for V. Same calculation. Okay? So if you want, this weird factors, coordinates we have are designed such that I get 0. You could also, if you want, rederive the definition by asking which coordinate should I have here so that when I do a dot product with U and V, I get 0, and you would get that. Okay? All right, so that explains a bit the weird definition. That's the right definition, so you're orthogonal to U and V. Now for the area, let's simplify the problems. I can always assume that UV, so UV forms a plane, okay? And I can always assume that they're in the XY plane. I just define my XY coordinates so that it fits, okay? And then let's pick the direction of V to be the x-axis. I can always do that. Then if I do that, V is simply in the x-axis, so I get V1, 0, 0, and for U, I get U1, U2 in the xy plane and 0 in the z direction. So if I do my cross product, I get minus U2, V1 in the direction of k, z direction. All right, therefore, if I look at the norm of U cross V, it's simply the absolute value of U2 times the absolute value of U of V1, because they could be negative, those coordinates. Okay? I look at my triangle. V1 is the base. And U2, if this is phi is the angle between U and V, U2 is simply U sine phi, okay, times, and V1 is also the norm of V, as I said. So U sine phi is the height, and this is the base. Look at the triangle. So height times base actually gives me the area. Okay? And this is why the dot product, the cross product relates its norm to the area of the parallelogram. All right. Little trivia question now. What is U cross U? U dot U, remember, was the length or the norm of U square. Now U cross U, well, it's the area defined by these two vectors, but these two vectors are, well, they're the same, so they're collinear. Same vector. And so the area defined by the parallelepiped is 0. So this is just the 0 vector. All right? You can check that this is true also if I do the cross product in the definition with itself. Well, I don't have U and V's, I only have U's. So I get U2, U3 minus U3, U2, 0. Same thing here, 0, 0. All right? So if you want to know if two vectors are so to know if two vectors are collinear or parallel, then I compute the cross product and I should get 0. 0 vector. Okay? And also, if they ask me a question, find a vector that is both orthogonal to U and V, well, I'll compute a cross product. That's one of them. All right, last thing is a triple scalar product. So we mix the dot product and the cross product. So I have, again, 3 vectors now in R3. And what I do the cross product with the dot product with U. Okay? Now, what is this? Well, the cross product between V and W gives me this vector. I use the right-hand rule of thumb here. And V cross W is orthogonal to both V and W. Okay? And the norm gives me the area. Now, what happens when I do dot U with that vector? Well, remember that the dot product of two vectors, now the two vectors are U and V cross W, it's the norm of U times the norm of the second vector, cross product, times the cosine between them, okay? The cosine between them, okay, cosine phi norm of U gives you exactly that height here, okay? If I put the two together, okay, the norm of the cross product gives me the area, Now I'm multiplying by u cos phi, which is the height. And so what I get is the volume of the parallelepiped defined by the three vectors. Okay? So think about that for a second. I have a parallelogram that's clear, and then I consider the parallelepiped that is defined by this vector and the parallelogram I had below. And the volume will be the area of the base, which is v cross w, times the height. So it will be exactly u cos phi times the norm of v cross w. And this is exactly what the dot product between u and v cross w gives you. All right? Now, I have problems pronouncing parallelepiped, all right? But if I use Google,
parallelepiped.
All right, parallelepiped. All right, and so you see a parallelepiped. It's essentially like not a cube, a rectangular kind of, but slanted, right? It's like a slanted prism. All right, so parallelepiped. Okay, so again, it looks complicated because, well, it's parallelepiped. It's a long word, and I also have many vectors and two operations. But really, what I'm doing is the area times the height. The area, again, is the norm of v cross w that we knew from above. Okay, and then if I look, so now I have two vectors, this cross product and u. If I do the dot product between the two, okay, that gives me exactly the projection on u, the norm of the projection of u on v cross w, and that gives me the height of the parallelepiped. All right? Okay, so that was for section 11.4. So thank you for listening.